All right, guys, so just as you're working here on this question, how do I start a question like this? Clayton? Okay, so if we can find the max and min, which are these values here, that should help us find A and C, right? So we know that A is max minus min over 2. And we know C is max plus min over 2. So that would be the starting point. Find the max and min. Okay. So I think maybe we can take these two up. Did everyone find these already? Okay, so what'd you guys get? Firstly, what is the max and min? Rebecca, what'd you use for your max and min? Okay, so max is 0, min is -1, and then what'd you get for A and C? All right, so A is positive half, then we do 0 plus -1 over 2, and we get -1/2. Remember, guys, C is the midline, so we're going to pencil this in. We're going to have to just sort of approximate it here, but it should be somewhere around here. Nope, C is the midline. Okay, what's the next step? What do we do? Rebecca? Okay. Mm-hmm. Cycle. Yep. Yeah, perfect. You can measure from a max to a max here. That one's probably the easiest to do the period. Great. Other ways that we can measure the period, we could measure from pi over 2 to 3 pi over 2, and then I would subtract 3 pi over 2 and pi over 2, so 3 pi over 2 minus pi over 2. I could also measure from, let's say, a rising midline to a rising midline. Probably not the best option for this graph, though, because we don't know exactly where those are. Minimum to minimum, max to max, any two corresponding points, as long as you have like a full cycle in there before the pattern starts repeating again. Okay. I asked you guys to start with cosine because cosine will be kind of the easier one to find D. So what did you guys do for D of cos? Rebecca? Okay, so we can pick pi. We could also just pick 0, right? Because the max is right on the y-axis. So I would probably go 0. If you put pi, that would be right too. But I think it's maybe simpler just to do 0 for D of cos. Other options, -2 pi, -pi, pi, 2 pi. We're just looking for a maximum for cos, right? Okay, here's the problem. When we go to find D of sine, we're looking for a rising midline, and that's happening like right here. And I don't know exactly what that value is. So last year we had a little trick to help us find D of sine when we have D of cos. Does anyone remember this? Bella? Right. So last year we did, to switch from a cosine to a sine function, we would do what the existing shift, so D of cosine, minus 90 over k. In radians, 90 is pi over 2. So that's what we're going to use for these. So I'll just do a couple little formulas off to the side here. So if we have the cosine and we want to go to sine, which that is our case here, the D of sine will be equal to the existing D of cosine minus, because the rising midline is always further left than the maximum is, so that's why we do minus, 90 over k was grade 11, grade 12, pi over 2 over k. So before I put this in, if I have pi over 2 over k, let's just simplify this because we don't want fractions inside of fractions. Flip and multiply, and we'll get pi over 2k. Okay? Worst comes to worst, just do pi over 2 over k, and then you can flip and multiply once you enter in the value of whatever k was. Okay, so it'll be minus pi over 2k. And you might be able to guess if we were to go from sine to cos, what would change? What would this look like? D of cos would be equal to what? Yep. So I'd do d of sine plus pi over 2k. Okay. So this one's nice because we have d of cosine is 0. If you chose your d of cos as pi, you should still get an okay answer. You'll probably just get this rising midline instead of this one that we're solving for, which is fine as well. All right, so I have the d of cos. I want to get the d of sine. I'm going to use this little shortcut here. So d of sine will be equal to the existing d of cos, which is 0, minus pi over 2 times k, which is 2. So 2 times 2. So I'm going to get negative pi over 4. Or in other words, pi over 4 to the left. Okay, so if you want, you can sort of just make sure you have these on your note. You can highlight, you can star them, whatever you need to do. This is only needed if we don't know exactly what one of the shift values is. That can help us find the shift value as long as we know one of them. So putting this in, yeah, Keaton?
I was wondering how you got the d of cos.
D of cos, we looked for the maximum. So in this case, the maximum is actually right on 0.
Just the last.
Yep, just looking for the maximum. Okay, so plugging these into our equations here. When I have pi over 4 to the left, I'm going to put plus pi over 4 in here. So that's the first one, and then we'll do the cosine one. Everything is the same except for phase shift, so the d value. And this one happens to be 0, so we're just going to write this as 2 times x. And you can just keep it, you don't need those square brackets or anything like that. You can just keep it as 2 times x, because we're not going to put minus 0 or plus 0 or anything like that. That doesn't make sense. So those are our equations. Emma. Thank you. All right, guys, so we'll continue when we get back. I'll see you at 10:15. So we're going to create a sine function with an amplitude of 7, period of pi, phase shift of pi over 4, and a vertical displacement of 3. So this one is similar to our graph ones, except it just lists the information instead of us having to pull it from the graph. So what does this tell us if we're creating a function? Kenzie? Okay, so our a is 7. What can we use the period for? Sam? Okay, so 2 pi over period, which is pi. So I'll get 2. Phase shift of pi over 4 right, Clayton? Okay, so d will be pi over 4, and then when we plug it in, it will look like minus pi over 4. And then the last one, vertical displacement of 3. This means that c must be 3. All right, so we're just going to plug it into our equation here. making sure we put in minus pi over 4 for the right shift. Okay, the question on the next page says, what if we were to create this but as a cosine equation? So I'm actually might just do it on this page here, but you guys can flip around to the other side if you want to fill it out down there. So what changes if this becomes a cosine function, and how do we figure out that change? Clayton?
The d-value will change, so you just link the pi over pi, or the d of sine plus pi over 2k.
Okay, perfect. So we have a cosine graph, and we want it to be, or we have a cosine equation rather, we want it to be a cosine equation. So we're going to use this. So I can find, I'll just do it down here. I can find d of cos by doing d of sine, so the existing shift, plus pi over 2k. So our existing shift is our positive pi over 4. And our k value we found as 2 above. So we're going to do pi over 4 plus pi over 4. What does that give us?
Pi over 2.
Yes, so it gives us 2 pi over 4 when we add the pi's, and then we reduce to pi over 2. So this is a pi over 2 right shift, right? All right, so we're going to plug in all the same things, except for we're going to change that d value. And it's going to be minus pi over 2 when we plug it in. Okay, any questions on those ones? Pretty similar to what we did for our graphs, but just with the information given rather than us pulling up the information out from the graph. Okay, we're going to do a couple examples of transformations, and then you guys will have some time to practice some of this stuff, okay? So we are going to graph the parent function and graph the transform function. Transformations, we will do the exact same way as we always do transformations, but we're doing it in radians, of course. So sine is our parent function. So if I look back at lesson 3, we took some time in lesson 3 to graph sine. And these right here, the 0, the pi over 2, the pi, the 3 pi over 2, and the 2 pi points are the ones that we're going to use as the key points for the transformation. So basically just the edges of all of those quadrants, right? Everything that separates out each of the quadrants. I don't need all the halves and negative halves and all the stuff like that. We don't need to use that many points. This should give us a good idea of what this looks like. Okay, so we're going to start with our parent function as always. So transformation rules, exactly the same. I'm going to say f at x equals sine x. And last year we used 0, 90, 180, 270, 360. So we're just using the radian values instead, is basically what I'm saying, which are these. Okay, and then, guys, you don't have to memorize these. They're stored in your calculator. You could use your unit circle for them as well if you wanted to. But if my calculator's in radians, I can literally just plug these in to sine in radians in my calculator, right? And I can get all the values. So as long as I know these, I'm good. Okay? We're not going to do transformations of sine, of tan. We're just going to do sine and cosine. So, yeah, Serena?
Are those points the same ones you use for cos?
Yep, we'll use the same ones for cos too.
And for tan?
Tan, we did use these ones, and we also would need more points, but we're not going to do transformations of tan anyways, so you don't have to worry about that for transformations. So if we were to plug all of these into our calculator, into sine, making sure we're in radians, we get 0, 1, 0, -1, and 0. These are our main points that we're going to transform. We are actually asked to graph 2 cycles of the parent function as well, so if you wanted to, you could extend this into the negative direction for your table of values, but I think we can just extend by looking at the pattern and extending back into the negative section. That was part of our homework from lesson 3. Okay, let's do the transformed function here. It's called y. I might just call it g at x here, so we can label it's 3 sine 2x minus pi over 3 plus 1. All right, how do I set up my transformation equations here? Same as always. Kenzie? Yep. 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 So that, what would that be here? Who can create these? Do you want to do them with the numbers? Plus, yep, switch the sign. And then the y ones? Perfect. So just as a reminder, if you're forgetting where these come from, these are I can write the little equations for us up here. 1 over k, reciprocal of k, plus d, and then ay plus c. Okay, I'm going to leave myself maybe some extra space over here as well so that we can use that space. We might need to do a little bit of fraction work because we have radian values here. Let's start with the y's. The y's are nice and easy. We're going to take all of these y's and plug each of them in here. So multiply them by 3 and add 1. Let's do that one quickly. So 0 times 3 plus 1, that'll be 1. 1 times 3 plus 1, 4. 0, we already calculated that one. -1 times 3 plus 1, -3 plus 1, -2. And 0, we already calculated, that should be 1 as well. Guys, if I have 3 zeros here, all of these should be the same, right? They don't get transformed into different values. I'm doing the same calculation on all of them, so I don't need to do it 3 times. I'm just going to plug it in for all of them once I calculate 1. Okay, let's do the radian side. So plugging in each of these x's in for x here. 0 times 1/2 plus pi over 3. That's just 0 plus pi over 3. That gives us pi over 3. 1/2 times pi over 2. So plugging in this one now. Plus pi over 3. I get pi over 4 plus pi over 3. If you need to do a little bit of common denominator work to figure out what this is, you can do that. So denominators of 12. This is multiplied by 3. This one's multiplied by 4 to create common denominators there. I get 7 pi over 12. Serena?
Do you want us to show that, or is it fine if we just put it in our calculator?
I mean, I think you should know how to do that, but if you don't show it, then I'm not going to make a big deal out of it. Some people, your calculator won't do that for you, so you may have to understand how to add fractions. Okay, next one, 1/2 times pi plus pi over 3. We get pi over 2 plus pi over 3. Common denominators. To get 6, I need to multiply the first fraction by 3. To get 6, I need to multiply the second fraction by 2. So we get 5 pi over 6. Okay, almost there. 1/2 times 3 pi over 2 plus pi over 3. So we're getting 3 pi over 4 plus pi over 3. Again, common denominators are 12s here. Multiply the left side by 3. Multiply the right side by 4. We're going to get 13 pi over 12. Okay, and then the last one, 1/2 times 2 pi plus pi over 3. The 2's will cancel, and we're really just left with pi plus pi over 3. So I'm going to create common denominators here. This will be 3 pi over 3 plus pi over 3. Just multiplying, think of this as if it's over 1. Multiply top and bottom by 3. And we will get 4 pi over 3. Okay, so a little bit of fraction work there. If you need to plug it into your calculator, of course you can do that. If you want to develop your math skills, it's never a bad idea to work on that yourself and be able to do it without your calculator. Common denominators, fractions, we know how to do this, right? Just create a common denominator, add the numerators. Same with radians, right? Doesn't change just because we have pi's in there. Okay, so a little bit more labor intensive to get these x's, but we're calculating transformations in the same way as we always do. So this question asks us graph 2 cycles of the parent and 2 cycles of the transform. So let's just start with the parent function here. That one's pretty straightforward. I'm going to graph 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, and 2 pi 0. That's one cycle. We can fill in the gaps here. Make sure your lines are nice and smooth curves here. If I extend this back into the negative section, it always goes mountain, valley, so I'm going to extend back into a valley. So imagine that you're sort of like just extending backwards like this, and you're going to follow the same pattern, right? So we're going to go negative pi over 2, negative 1, extending back here, and then just continue the pattern here. Go up to 0 at the next one, which will be negative pi. And if I'm really not sure, plug them into your calculator. Calculate sine of negative pi over 2, should give you negative 1. Calculate sine of negative pi. Calculate sine of negative 3 pi over 2. Or if you're good with that visual, kind of looking at the pattern and seeing, just continue the pattern up. Okay, and then the last section here, down here. If I've done this correctly, it should look nice and mountain, valley, nice smooth curve, everything equally spaced, all of that kind of stuff. Okay? That's the parent. Same as what we did in degrees, right? Should look exactly the same. Okay, so you might be asking yourself now, how do I graph all of these values? Which is a good question. So part of what we need to remember is that, like, when I give you these graphs, I'm going to give you the labels like this. I did that on the quiz as well. The scale is still the same as what we did in class. So if you have your circle, which many of you guys just filled out at the front of the quiz, this is all going by pi over 6s, right? Like this is pi over 6, pi over 3, pi over 2, and we're just counting up by pi over 6s. So really what I'm doing, guys, is I'm doing 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, and then we're just reducing. So if it's helpful, you can put in these values if you need to. Okay, 5 pi over 6, 6 pi over 6, 7 pi over 6. This one's 8 pi over 6, which will reduce to 4 pi over 3. 9 pi over 6, 10 pi over 6, reducing to 5 pi over 3, 11 pi over 6, and this is 12 pi over 6. And you could continue if you needed to. So there, I have a couple values in this. So pi over 3, I know where that is. I know where 5 pi over 6 is, and I know where 4 pi over 3 is as well. So here, the key relationship is that 1 unit on the x-axis equals pi over 6. 2 units, what's 2 units on the x-axis? Pi over 3. This is going to help us figure out where these values go. What would be pi over 4 if I needed it? I don't have any pi over 4s here, but if I needed pi over 4, what would that be? Yeah, it's like 1.5. That's like pi over 4. It would be like 1.5 units on the x-axis. Not useful for this question, but maybe useful for other questions, right, that have the same scale. So 1.5 units on the x-axis is pi over 4. Okay, what's the relationship between pi over 6, and we have a bunch of pi over 12s here? What's the relationship? Bella? Okay, great. So if pi over 6 is 1 unit, how many units is pi over 12? Half a unit. Okay? Pi over 12 is half of pi over 6. So pi over 12, we need that information here. 0.5 units on x-axis equals pi over 12. Okay, so why am I saying all these things? Well, this is going to be useful for us to know when I think about where to plot all of these, right? Okay, so pi over 3, we already labeled that on here, but it's going to be 2 units on the x-axis. It's 2 over. And we're going to plot that at 1. So pi over 3, 1. There it is. Do this in red. Okay. 7 pi over 12. Where in the world do I place this? Well, if I know, yeah, Sam, do you have an idea? Okay, great. So what I like to do is if I know pi over 12, so basically what Sam said, if I know pi over 12 is 0.5 units, and I have 7 times pi over 12, I'm going to just do 7 times 0.5 on my calculator, and then that will tell me how many units I need to go over on the x-axis. So I go over, what's 7 times 0.5? 3.5. So I'm going to go over 1, 2, 3.5, and that should have a y value of 4. Okay, so I'm going to plot that up here, right here. So that is 7 pi over 12 right there. 3.5 units over. 5 pi over 6. We have this one labeled. Also, if we know that pi over 6 is 1 unit, if I have 1 units, then I have 5 units, right? So you can just count over 1, 2, 3, 4, 5, and plot that at 1. How do I figure out what 13 pi over 12 is? How many units is that on the x-axis here? Okay, so 13 times 0.5, 6.5 units. So count it over. 1, 2, 3, 4, 5, 6.5 has a value of -2. So I'm going to go down here at -2. It's right in between pi and 7 pi over 6. Okay, and then last one, 4 pi over 3, we have that labeled, but we also know that pi over 3 is 2 units. So if I do 2 units times 4, that's 8 units, right? So go 8 units over and plot that at 1. It's already labeled for us. We already did the labels, so that's good. So there's our 1 cycle here. We need 2 though. So we need to just keep continuing the pattern here. How many units apart are every single one of these points? Sam? They are, so if I count from here to here, these are all 1.5 units apart. As soon as I figure out the number of units the first 2 points are apart, I know the number of units for all the rest of them, right? I'm just going to keep adding that value. So all of these units, this was 2 units. This one was 3.5 units that we calculated. This one was 5 units. This one was 6.5 units. And this one was 8 units. I should be noticing that all of these are adding 1.5 units every single time. So I don't even need to go through the whole process of finding out what the units are for all of them. If I find out the difference between the first 2, that's going to be the difference between the rest of them as well. It's all equally spaced. So I'm just going to keep going 1.5 units. So from here, count 1.5 units and continue the pattern. So just like we did with our graph. So going up. So now I'm going to go up. And I'm going to plot right here. 1.5 units over. 1.5 units over now from there, back down to 1. So here's the first part. Continue the pattern. Down to the next one. Count 1.5 units over. 1.5. Down at negative 2. Should be right here. Okay, so following along with this pattern here, continue down. Okay, and then the last one, count another 1.5 units. There's 0.5 and 1, and that should be up at 1. So just, again, completing that cycle there, back up to where we started and ended. There it is. So we'll call that g at x. This can be f at x. Okay, a little tougher to plot the x-coordinates in radians. I recognize that. That's why we're going over this, and we're taking our time with the x-coordinates here. Shall we try one more, just so that we can get the hang of the units and stuff like that? Okay, so parent function is cos. We're going to use the cos key points. I'm just going to call the parent function f at x. Same x-coordinates, 0, pi over 2, pi, 3 pi over 2, and 2 pi. When I plug these into my calculator, which you can do, just make sure you're in radians, you should get 1, 0, negative 1, 0, and 1. New function. Half cos half of x plus pi over 4 minus 2. So who can set up our equations for us here? I'm going to leave some space for the x's over here. Bella? Great. Let's do the x's first quickly here. Half of 1 minus 2, so half minus 2, negative 1.5. 0 times a half minus 2, that's just negative 2. Negative 1 times a half, so that's negative half minus 2, negative 2.5. And then 0 and 1 will be the same as the ones I calculated above. Okay, x coordinates. Plugging in each of these in here. So 0 times 2 minus pi over 4. That's just going to give me negative pi over 4. How many units did we say pi over 4 was if I'm going by pi over 6's? If this is like pi over 6 and pi over 3 and pi over 2? Pardon? 0.5. 1.5, because it's in between pi over 6 and pi over 3. Also, guys, another thing that you can think of is that pi is 6 units. So if I know that pi is 6 units, I could literally find any number of ticks that I want here, right? Because if I know what pi is, if you just find pi, to calculate the units, I'll just do negative 6 over 4, and that will tell me the number of units on the x-axis, because pi is 6 units on the x-axis. So to calculate units, maybe the easiest way is just do negative 6 over 4 on your calculator, and you'll find the number of ticks that you have to count over on the x-axis to plot your point. Does that make sense? So this one should be negative 1.5 units on the x-axis. Okay, let's keep going. Pi over 2. So 2 times pi over 2 minus pi over 4. That's going to give us pi minus pi over 4. Common denominator, 4 pi over 4 minus pi over 4, we get 3 pi over 4. Calculate your units. Let's just use the pi equals 6 units. That's probably the easiest way. 3 times 6 over 4, how many units is this going to give us on the x-axis? So I'm just plugging in 6, the number of units that pi is. I'm plugging in 6 for pi because pi is 6 units. Rebecca? 4.5. 4.5 units. Great. Let's keep going.
How did you get 3 pi over 4?
So this is, if I create a common denominator, this is 4 pi over 4, and then I subtract pi over 4. Okay, 2 times pi minus pi over 4. This is 8 pi over 4 minus pi over 4. That will give me 7 pi over 4. Okay, calculate the units. What's 7 times 6 over 4? Bella? 10.5? Okay, what's the pattern, guys? Because I don't need to keep doing this, right? What's the pattern between the number of points in between each unit? Or number of units in between each point, I should say. 6, I'm adding 6 every time, right? So I don't need to keep calculating this. I'll just add 6 every time. So let's just finish the last 2 here. 3 pi over 2 times 2 minus pi over 4. 2's will cancel. I'll get 3 pi minus pi over 4. If I create a common denominator here, 3 pi is 12 pi over 4, right? That will give me 11 pi over 4. If I add 6 units, I get 16.5 units, right? We're just adding 6 every time, plus 6, plus 6. And then last one, 2 times 2 pi minus pi over 4. This is going to give me 4 pi minus pi over 4. Common denominator, 16 pi over 4 minus pi over 4. This is 15 pi over 4. Add 6 units. This is 22.5 units on the x-axis. Now that we know all the units, this should be easy. We're just going to count, right? That's all we need to do. So 1 cycle of the parent function, 0, 1, just graphing this function here, pi over 2, 0, pi, negative 1, 3 pi over 2, 0, 2 pi at 1. There's the parent function. I'll call this f at x is cos x. Then I'm going to graph at negative 1.5 units on the x-axis. I'm going to graph negative 1.5. So I'm going to count over 1.5 units to the left, and I'm going to plot that at negative 1.5. It's about right there. The next one says 4.5 units. So 1, 2, 3, 4.5 at negative 2. So plot that down at negative 2. Next one says 10.5 units. So this was 4, 5, 6, 7, 8, 9, 10.5. Plot that at negative 2.5. So we're just counting 6 units over every time here. Okay, next one, 16.5 units. So this was 10, 11, 12, 13, 14, 15, 16.5. Back at negative 2. And I can't fit 22.5, so I can't fit that full cycle here. So we're just going to plot it 6 units to the left of this one. That should be the same, right? Because it's a full cycle apart. So I'm going to count over 6 units. 1, 2, 3, 4, 5, 6. This one should have the same value as this, 1.5. No, sorry, same value as this one, because it's a full cycle apart. So right here. Okay, we can't fit two cycles on this, so we'll leave this as 1 cycle.